In this session, we will explore the Circom language, a framework for creating zero-knowledge proof circuits. The session is structured into two parts. Part 1 focuses on setting up the programming environment, and Part 2 delves into the syntax of Circom. As a quick review from our first course, zero-knowledge proof is a protocol between two parties, the prover and the verifier. The prover needs to show that she has specific knowledge without revealing the details. She starts with secret data, known as the input. After running a program, she generates both an output and a proof. These are sent to the verifier, who examines the proof. If the proof is valid, the verifier accepts the output. Remember, the prover is responsible for handling the input, program, output, and proof. On the right side, the elements available for the verifier's verification are displayed, which include the program, output, and proof. Let's break down the zero-knowledge proof process into simpler terms for developers. We start by writing a high-level language. Next, the ZKP circuit compiler transforms it into a low-level program. The witness generator receives the circuit and private input, then generates a witness. Subsequently, a proof generator runs the code, producing both the proof and the output. On the verifier's end, there is a component known as proof verification. Its role is to check the proof and determine its validity. This streamlined overview aims to facilitate understanding of the core software components in ZKP without delving into technical terminology. The first two tasks are performed using Circom tool, which I have colored in green, while the proof generation and proof verification are handled by Snark.js, which have a different color in this slide. Let's review the actual file formats for the input and output of each software component in this process. The program is written in a file with the extension .circom. This file is fed into the Circom compiler, which generates several files. For our purposes, we use only two of them, a .r1cs and a wasm file. Additionally, the input is written in a JSON file format and then fed into the witness generator. The output file extension of the witness generation step is .wtns. The proof generator receives the witness file and generates a proof and an output in JSON file format. Finally, the proof verification process receives them and verifies the proof. Before we proceed, it's crucial to recall that in some ZKP systems, a key generator is used to create the keys for both the prover and the verifier. With this review in mind, we are now ready to set up our environment. The core tool is the Circom compiler, which is written in Rust. To install Rust on your system, simply go to the Rust website to find the right command and procedure for your computer. To start, we assume that you have a copy of Rust on your computer. Therefore, we start by installing Circom on your machine. To start, we get a copy of Circom from GitHub. We type git clone https github.com/idn3/circom.git. Then we go to the folder cd circom and build the project cargo build double dash release. Next, we install the project cargo install --path Circom. Then we install Snark.js using npm. npm is a package manager for the JavaScript programming languages. It comes bundled with Node.js. To install npm, you can simply go to the Node.js website to learn how to install it on your machine. For this course, we assume that you already have npm package manager on your system. Therefore, we continue by installing Snark.js. I type sudo npm install -location global Snark.js. I enter my computer password. Snark.js is installed on my computer. My system is ready to compile a Circom program. Our first program is Fibonacci series. Fibonacci series is a sequence of numbers where each number is the sum of two preceding ones. For example, if the first element in Fibonacci series is 1 and the second element is 2, therefore the third element is 1 plus 2, which is 3. The fourth element is 2 plus 3, which is 5. And the fifth element is 3 plus 5, which is 8, and so on. Now, as another example, if we consider the first element as 1 and the second element as 17, the next element would be 1 plus 17, 18. And the fourth element would be 17 plus 18, 35, and so on. Now assume the prover has a secret X that she does not want to reveal or share with verifier. However, she claims that she knows X as the second element of a Fibonacci sequence, such that the 1000th Fibonacci number is equal to this large number. We put these two elements, 1 and 17, in input.json file and this large number as the output in output.json file. Prover has input.json and output.json files, and verifier knows only output.json file. This is the input.json file on my machine, and this is the output.json file. Now let's go and review the code. Every Circom code begins with the directive pragma Circom. It then specifies the Circom version, which in our case is 2.0.6. Each Circom program contains only one main component. We write our code within a template, like this one, template Fibonacci, and assign it to the main component. Here is the Fibonacci code. For now, let's go to Visual Studio Code and save this code in a Circom format file. This will allow us to proceed and first understand the command for proof generation and verification. Later in this session, we will review the code in detail. So far, we have the Fibonacci.circom file. Now, we will use Circom to compile our code. We have Fibonacci.circom file in this folder. Now I type Circom Fibonacci.circom --r1cs --wasm After compiling this code, Circom generated .r1cs version of our code. Also, Circom generated a folder called Fibonacci_JS. Inside this folder, you see Fibonacci.wasm and also two Java scripts called generate_witness and witness_calculator.js. So far, we have these two output files. Also, remember, from the previous step, we had input.json file. The next step is witness generation. We first copy the files from Fibonacci_JS folder to the main folder. Copy Fibonacci_JS star space dot. I move these files to the main folder. I run the following command to generate the witness file. Node generate witness.js Fibonacci.wasm, then input JSON, and we specify the file name for the witness. I call it witness.wtns. Enter. The witness file is generated now. So far, we have obtained the witness file. Now, we need to create the prover and the verifier keys using the key generator. We can use either Grout16 or Planck for this process. We discussed these two methods in course 1, and you should be familiar with their differences. In this example, I will use Grout16, which consists of two phases. Phase 1, powers of tau. Phase 2, circuit-based key generation. The first phase is circuit independent and can be executed using the following two commands. snark.js powers of tau new bn12812 pot. I give a name to our generated file, pot120.ptau. When I enter this one, as you see, Snark generated this new file. The second command is snark.js powers of tau contribute our first file, which is a pot 120 tau power of tau, and our new file can be 121 power of tau. I give a name for this version of our code. I enter a random text. Okay, the first phase is done. The output file contains both the proving and the verification keys. Now we can proceed with the second phase using these three commands. snark.js, again powers of tau, prepare, phase 2, pot 121.power of tau, pot 12, final dot p tau dash v. The second command in phase 2 needs the r1cs file. I type snark.js Grout16 setup, then Fibonacci.wasm r1cs, the generated key file, which is a pod 12 final, p tau, then prover verifier 0 dot z key, enter. The third and the last command for phase 2 is snark.js zk contribute power prover verifier 0 dot z key, then a new file, I call it prover verifier 1 dot z key, and the name is first contribute name -v. I enter a random text and it's done. Finally, we export the verification key using this command. snark.js zkey export verification key prover, then verifier 1.json. The keys are generated. Now that we have generated the prover and verifier keys, we are ready to generate the proof. We generate the proof using the following command: snark.js growth16 proof, then prover verifier 1.zkey, then witness.wtns, and we specify the name for our proof and another name for our output file. Okay, the proof and output file are generated. The output and proof have been generated. Now it's time for verifier to begin the verification process. If the proof is valid, the verifier accepts the output. Otherwise, the verifier rejects it. Verifier now verifies the proof using this command: snark.js growth16 verify, then verifier 1.json, then output JSON, and the proof JSON. The proof is confirmed. Therefore, the verifier trusts the output. We now understand how to generate a proof and verify it.